Okay, we know that when we downsample a signal or sequence by a factor of m to get xd of n, then aliasing can take place. And we have seen that the only way to avoid aliasing is that xn is band limited. So avoid aliasing by ensuring that x of n is band limited to pi over m radians per sample. Okay, so the question is, what if xn is not band limited to pi over m radians per sample? What should we do? In the continuous world, we know what we should do if there is danger of aliasing. We low pass filter our continuous time signal by an anti-aliasing filter that has a cutoff that is pi over t. So we make sure that we don't have any frequency more than 1/2 of our sampling frequency. That's what we do in continuous time. Okay, so in continuous time, aliasing is prevented by using a low pass filter. Well, it turns out that in this downsampling operation, where we don't want to go into the discrete world, we actually can do the same thing. We can avoid aliasing by using a digital anti-aliasing filter. What is that filter? That filter is again a low pass filter. So it's a low pass filter with cutoff of pi over m and gain equals 1. So which is equal to that we have a Fourier transform h of e to the j omega, which is 1 for all frequencies between pi over m and 0 for frequencies between pi over m and pi. Okay, so we can do the same thing, and what that means is that in the discrete world, before we do downsampling, what we should add is a low pass filter. When we know that we are going to downsample by a factor of m, we should add a low pass filter which has a cutoff of pi over m, and the gain of that filter is 1 because we don't want to touch any of the other frequencies. The output of that filter will be x tilde n, and then we can downsample by a factor of m to get x tilde d of n, which is basically x tilde of nm. Okay, so in the world of digital signal processing, this whole block is sometimes referred to as decimation. While some authors use decimation and downsampling interchangeably, in many cases downsampling is reserved for only this version, whereas decimation is used when actually you precede the downsampling block with a low pass filter that has a cutoff of pi over m and gain of 1. Okay, now if there is so the things to keep in mind here are that if xn is band limited to pi over m, so if the input signal was band limited to begin with, then we know that low pass filtering is not going to do anything to it. So in that case, x tilde n will be equal to xn, which means that your downsample version will actually be the same as if you had no low pass filter, so you will get xn of m. So the advantage of adding the low pass filter is that you get back what you desired if there was exactly a band limited signal. And if xn actually came by sampling a continuous time signal xn of t, then in that case x tilde d of n will be equal to the sample of your original continuous time signal sampled at a higher sampling time or lower sampling frequency. Okay, but if xn is not band limited to pi over m, then this won't be true, of course. X tilde dn would not be equal to x of nm, but at least the advantage is that we have avoided aliasing. Now, the other thing to keep in mind in this case is that when is xn not band limited to pi m? If xn is not band limited to pi m, then this implies, this is if and only if, your underlying continuous time signal x of t was not band limited to pi over mt. So by this time, hopefully we are very comfortable in going from discrete frequencies to continuous frequencies and back. So if your original sequence is not band limited to pi m, then your original continuous time signal was not band limited to pi m over t. And this low pass filter in that case means that your new sequence x tilde d of n is no longer the samples of your continuous time signal, but it is related to your continuous time signal still. How is it related? Well, since we are low pass filtering, xn by cutoff frequency of pi over m, this is equivalent to, since xn is samples of x of t, this is equivalent to saying we are low pass filtering x of t, the original continuous time signal, by cutoff frequency of omega c is equal to little omega c over t, which is pi over mt. So adding this low pass filter is in the discrete domain is effectively adding a low pass filter and anti-aliasing filter in continuous domain. And so this means that actually x tilde d of n, your downsampled version, is, this corresponds to samples of a low pass filtered version of x of t. And that's the best that we can hope for, because x of t we want to downsample, we want to get to a sampling rate of mt, or rather we want to get to a sampling rate of 1 over mt and sampling time of mt. Well, if that is the case, and if your signal is not band limited to pi over mt, if it does not satisfy this, then we have to pass it through an anti-aliasing filter, and that is what this discrete filter does. So in discrete time, whenever you want to use downsampling, you should precede it with a low pass filter to avoid the aspect of aliasing. Now, does this aliasing happen without any price? No, we pay a price. We are throwing away some frequencies, but that is better than corrupting. That is better than having those frequencies fold into other frequencies and corrupt our other frequencies. So let's take an example of decimation of a sequence by a factor of 2. So we are given a sequence whose Fourier transform is as shown in this figure, and we want to do decimation by a factor of 2. So the first thing that decimation involves is we will low pass filter this thing by an ideal low pass filter with cutoff of, since it's by a factor of 2, our omega c is equal to pi by 2. So our low pass filter, let's say that this is our low pass filter. It goes up to pi by 2 minus pi by 2, and similarly it will, of course, low pass filter the other periodic repetitions. Okay. So when we do the low pass filter, we will get the Fourier transform of x tilde of n in the above expression, so before the downsampling operation. So once we do the low pass filtering of the original sequence, this is what we get out of this. Now we are going to downsample this thing. So decimation involves low pass filtering, downsampling. Now we are going to downsample this by a factor of 2. And in a previous video, we saw what is the relationship now between the sequence that is downsampled, that's Fourier transform, and the new sequence is Fourier transform. So what we are going to do is we are going to simply scale the minus pi to pi version of this sequence by a factor of 2, scale the magnitude by a factor of 1 by 2, and then we are going to periodically repeat that, and we'll get back our final expression. So let's do that scaling. So first of all, this thing will get stretched, and the height will become 1/2. So this will become, this pi by 3 will become 2 pi by 3. So it will go up to 2 pi by 3, and then it's going to get all the way down to this point, which is going to be 1/2 of whatever is this value. So this height will be 1 by 2. This point is going to be 1/2 of this circle. Similarly, this is going to come down, and this is my stretching of whatever is the frequencies, whatever are the frequencies between minus pi and pi. And then I will have a periodic repetition of this thing. So I'll go up, do the same thing around pi, 2 pi, do the same thing around minus 2 pi, and so forth. Okay, so this is, when I do decimation, this is what I will be having. This is my pi region, minus pi to pi region. And this plot, basically, if we did not do the low pass filtering, we would have had severe aliasing from pi by 2 to pi region, because that pi by 2 to pi region will have stretched into pi to 2 pi region. So we already saw in a previous video what that effect would have looked like. So decimation effectively ensures that we do not have folding of the frequencies that we cut off into other frequencies. We have lost some information here, but that is better than corrupting all these frequencies that we have been able to retain. In a computational software such as MATLAB, there are different commands that distinguish between decimation and downsampling. So you can play with that. You have to pay attention to which one only does downsampling and which one does downsampling but preceded by a low pass filter.